everyone had a good chance to get some of the things needed to get done over these past few minutes. And it's my pleasure to introduce Rick Stevens, the Associate Lab Director for Argonne. Rick, thank you for joining us.
Hi. Okay, so let me bring up my screen a little bit here. All right, so what I'm going to talk about is what's happening in the US on the march towards exascale, and then some of our thoughts about what that means in terms of linking HPC and AI together, and kind of little hints as to what we're thinking kind of over the next 5 to 10 years a little bit. So that's, and I'll have you to answer questions. I have a lot of stuff, but I'll try to go fast. So let me briefly update you on what's happening with the DOE exascale systems. So this is a roadmap chart, a little bit busy, kind of showing major systems at the DOE labs over the last few years, and putting kind of in a timeline here the installation of Frontier, which is going into Oak Ridge right now, the Aurora system, which will start being installed next year, and then the LCAP at Livermore. These are three kind of flagship exascale machines being installed in the US. There's an NSF program to build out another big kind of leadership class machine at Texas that you'll have to talk to Dan about details there. But the three DOE lab machines, and there's other machines, of course, there's machines at Berkeley and at Los Alamos and Sandia and so on, but these are three of the biggest ones, are remarkably similar. They're GPU accelerated x86 based machines. Ours is Intel CPUs and Intel GPUs. The Oak Ridge Livermore machines are AMD CPUs and GPUs. And almost accidentally, these machines are going to be really great at both simulation. They have high, FP64 performance, but incredibly high lower precision performance that'll be extremely useful for AI. So we kind of lucked out in that the architectures we've been working on for the last 4 or 5 years are turning out to be really great hybrid platforms. Frontier is, you'll get some updated specs probably in the next couple of weeks from Oak Ridge, but it's a peak machine, a little over 1.5 exaflops. It's about 9,000 nodes. It's AMD CPUs with 4 GPUs, MI200s in there, and then a hybrid memory architecture that has both DDR on the node and HBM on the GPUs, and then some fast storage, non-volatile memory for local caching and so forth. It's got 4 network ports per node, Dragonfly topology integrated by HPE, and the power budget's maybe 30-ish megawatts. What's really interesting is that back when, we've been working on exascale since 2007, and the first kind of predicted machine targets that we had around 2009, we predicted out what exascale would look like, and we were pretty close, kind of 10 years ago, with what the exascale machines might look like. We're more or less close to the power target, about 20 megawatts per exaflop. We're probably a little bit lighter on memory, hasn't evolved as fast as we wanted. Node concurrency is a bit higher because of the GPU technology, but the overall concurrency, of course, was bounded by clock rates at about 1 billion. And so things are not bad. They're I would say, more or less similar to what we estimated 10 years ago. Whether this will continue to be true as we look forward is not so clear. Aurora is, of course, similar to these machines. We've been working with Intel for quite a while on it. It's GPU based. It's the new Intel GPUs, what they call Ponte Vecchio, which they've announced at the Hot Chips recently. And we've kind of optimized the design point to be good at simulation, data processing channels like for sensors or for imaging off of light sources and things like that, as well as for massive AI training and inference. And so it's a sweet spot. It's being assembled by parts by Intel and integration by Hewlett Packard and funding by DOE and installed at our site. This is what our node looks like. It's got two Sapphire Rapids CPUs with a total of order 100-ish cores between them, and then 6 GPUs, all programmable in this one API software infrastructure that Intel's building that allows portability between code written for the CPU and GPU and other things. Has a unified memory architecture between the CPUs and GPUs, and a really fast backend network that connects the GPUs together. And then we have 8 network links out of the nodes. So we have about twice the number of network links as the Frontier machine. LCAP is based on a next generation AMD infrastructure. It hasn't been really publicly disclosed yet, but it's a similar evolution of the Oak Ridge design point. The first applications on these machines are going to be these exascale applications being developed as part of the DOE Exascale Computing Project. There's about 25 application targets. Sometimes there's several codes within each of those buckets, and it spans the whole suite of things you might imagine high performance computing being applied to in traditional simulation sense. Everything from material science, quantum mechanics kind of problems, chemistry, cosmology, earthquakes, geoscience, power grid work, cancer research, which is really more deep learning. It's one of my projects, metagenomics analysis, light source stuff. So lots of application diversity. All of these teams have been working for the last 4 or 5 years, tuning and building codes, optimizing them for GPU hybrid machines. Most of these, or almost all these, are running on Summit now in the system there on the V100s, but also a lot of these are running on current intermediate machines with other GPU installations. Behind all that is an integrated software stack that has about 80 packages in it, ranging from programming model support, pretty much all the programming models that you can think of, abstraction layers built on top of CUDA or built on top of one API or on top of the infrastructure that AMD is building, multiple versions of MPI and so forth, out of compiler infrastructure, tools and technology for auto-tuning, math libraries, visualization libraries, data management libraries, and things into the ecosystem. And essentially all of this is open source and has been being built kind of nightly for the last couple of years in our various servers. And this is something that you guys might want to leverage as much as possible. I mean, it's all open, but trying to leverage it as a stack is quite interesting because we're debugging it, running it together as a stack. So the cross-compatibility issues are all being worked. As we think forward on the hardware, let me see if I can manage my slides here. We're thinking there's probably 2 more drops, and we're trying to move to a model that allows more continuous upgrade action, but maybe in 26 drops that are kind of order 10 exaflops for FP64, maybe 100 exaflops in things like BFP16 for AI. And then maybe by 2030, we think it might be possible to get to around 50 exaflops in simulation mode and maybe a Zeta op for AI ops in BFP16. These are kind of targets. We don't have any vendors yet signing up to this, but this is more or less where we're going with RFIs coming out this fall that will kind of give guidance to the vendors. Now, we're trying to integrate what we want with what's possible. And I have a shortened version of this talk in this one. I have a longer version where I talk about silicon roadmaps, but I will skip that. One open question is the new market for AI accelerators going to augment these designs or somehow replace or GPUs or somehow be augmentation? We're not sure whether the future systems will support 2 kind of processor hierarchies like the current systems, CPUs and GPUs, or whether they'll support 3 hierarchies, some kind of CPU, some kind of general purpose accelerator, some kind of AI accelerator. So that's one of the big open questions. I'll talk more about that in a few minutes. We're also asking the vendors about quantum. We don't think it's going to hit certainly in the 26 timeframe, it's not going to be relevant, but maybe by the 2030 timeframe, it might be. About a third of the cycles on the big DOE machines are used in some kind of quantum oriented simulation. And we think that might be the sweet spot for the early quantum machines in terms of offloading things. But that's still a lot of R&D in that space. And we don't think in the 26 timeframe that mainstream vendors will pitch quantum as part of their offerings. At least that's what we're seeing right now. A Chinese group has proposed a roadmap to Zetascale by 2035. I think this is a really interesting exercise. They spec'd out a machine. I did some math on the right here in red that showed how much compound annual growth rate we'd have to have against the current system deployment targets we have to hit Zetascale by 2035. And some of it's pretty amazing. Like, for example, the peak performance would have to grow at about 60% per year between now and 2035 to hit this goal, and so forth. You can read the numbers here. I'll make these slides available. Some of these are somewhat unlikely, right? These compound annual growth rates of 60% in networking or storage capacity are unlikely. Power, maybe 100 megawatts. We obviously, if we think bounding at 100 megawatts is not unreasonable. But some of these are pretty aggressive. So Zetascale is not going to be easy. And it's at least as hard as we thought Exascale was back when we started in 2007. So that's kind of sobering. Let me talk about AI for science. So back in 2019, pre-COVID, we started a big workshop series. Kicked it off at Argonne. We had sessions at Oak Ridge and Berkeley and then Washington, trying to bring the community together around what we viewed as the next big thing after Exascale, which is this notion of a major initiative around bringing AI into scientific domains and scaling everything up and coupling it to simulation as well as big data-oriented problems. There's a report that we put out in February of 2020 that has the results of the initial work here. So it lays out research opportunities in AI applied to scientific domains, biology, chemistry, materials, climate, so forth, as well as AI applied to running systems, big systems design, software lifecycle, and so on. We modeled this after the workshops that got us to Exascale, and we're kind of hopefully exiting COVID nightmare. We'll be relaunching a series of workshops to build out the program plan for this. So that's work that's ongoing. And we actually have some connections into the UK via Tony Hayes' effort and some conversations with Turing and others about being part of this broader initiative. So that's ongoing. Now, of course, we're also tracking and some of us are working in deep learning and trying to understand where this is going. Now, there's been huge progress. I don't need to tell you kind of about that. And things are starting to bleed over into science areas like AlphaFold, which is really starting to have major impact on the biomedical computing space. We've got some servers set up to predict structures for our structural biology community and for our drug design efforts. But one thing that we're really tracking is the evolution of general purpose language models, because we think that transformers and in general, this progress on these large models are indicative of broader trends in how AI is going to mature in other domains. Of course, in language, there's been huge progress. Beating benchmarks having to result in harder benchmarks to work on. Transformers, which have been very successful in languages, are also working in other domains like imaging, and computer vision, and other problems. And I don't have time to dig into how these work, but they're I think, an indication of the future. Some of these have been applied to problems in mathematics, like this group at Facebook that built a sequence-to-sequence type of problem solving system using an AI method to essentially learn how to do integration, symbolic integration. They trained it by a massive database generated by forward automatic differentiation systems. And the cool thing was that it was able to solve problems and generalize beyond the expectations of the authors. So it could be that mathematics is kind of an extension of language problems, and these big transformer models we think are probably likely to be able to be used in mathematics as well as classical natural language. They're already being used in code generation and code translation, which we think is an indication of the generality of this. Not without some controversy, but in terms of how GitHub is using this. But this is also very relevant to the scientific communities in terms of code optimization, code porting. So we think there could be real opportunities in computer science using this kind of technology to help ease the software burden and increase efficiency on machines. There's recently been work done in China and at the Beijing Academy for AI that trained what we think is probably one of the world's largest models, about 1.75 trillion parameters. And this is a transformer model that implemented a fast mixture of experts technique. So it's really a whole bunch of submodels that get gated by the type of input as they come in. But this single trained model achieved essentially state of the art in multiple benchmarks. And we think this is a real indication of progress and steps towards more general AI systems, and something that we're tracking very carefully. The way this works is that single language models, big transformer models have kind of maxed out at maybe a couple hundred billion parameters. But what they did here is they have many submodels, and as things are being trained, the network learns how to invoke certain submodels for each type of data that it's learning. And so it's really implementing a form of sparse learning, and it's more efficient than if it was a single dense model. So this may be one way forward. Now, we're also seeing a huge amount of progress, and some of this was discussed by the last speaker, I think, in this general notion of using AI to accelerate or replace or augment simulations. And the basic idea behind this, of what we call machine learning surrogates, is you have some system, say a classical simulation of it, say some ODE solver, PE solver or something, and you go into the internals of that and you capture the input-output relationships of certain functions, whether they're, as you were talking about, subgrid scale parameterizations, as it might be a climate model or a cosmology model or something like that, but it could be any function really. You generate training data, you then train a surrogate machine learning model, and you plug that back in and you run this. And when you do this, you get considerable speed ups. And if you can bound the errors, it's a very effective way of searching large spaces. This has been used in many areas, but in material science, it's being used, say, to search for materials with certain properties. So you build this model, you train it on, say, a bunch of electronic structure calculations from a set of examples. You learn that function. You then sweep through a much larger set of configurations, predict the properties, sort it, kind of enrichment, kind of like the way you do enrichment in, say, drug design. You then capture the high-performing compounds or materials that you care about, and then you run the classical simulation. And by that, you can search a much larger space. We see this happening around the world in lots of applications. So this group in Edinburgh and in San Diego and the Netherlands show that you could get massive speedups in chaotic three-body problems, and they claim a acceleration of up to 100 million times on some problems. So that's pretty impressive. The group out of Oxford that you guys probably know about did a very interesting example here where they built a single model architecture, trained it on data from many different applications, really didn't tweak the architecture that much, and then showed that you could get acceleration against many areas, and in some cases up to 2 billion acceleration, which is pretty interesting. We've done a similar thing in drug development, my group, where we accelerated our drug docking codes initially by about a factor of 50,000 using a deep learning model. And then later, by collaborating with Grok, one of the AI hardware startups, we got that up to 11 million acceleration. This is for the drug docking problem, where you've got small molecules docking into a protein. At 11 million X, you can search a library of, say, 4 billion compounds in less than half an hour. And it completely changes how you think about the problem. So this idea of surrogates accelerating simulations is a particularly interesting thing. It means that an exascale machine effectively becomes a zetascale or maybe a yotta-scale platform for many problems. And that is a very exciting thing to work on. Now, others are looking at how AI can be used to change the normal workflows in things like, for example, climate modeling. So this is a group at Caltech that's doing this, where they're basically plugging AI into the different stages of the complex workflow that takes Earth observation data, maybe does data assimilation, maybe does subgrid scale physics, and AI for analyzing the output of climate. So this is a pretty interesting approach at kind of embedding AI in there. And DOE's got a big initiative on this called AI for Earth Science Prediction, that's going to have a series of workshops starting in a couple of weeks. We got over 700 people involved about how we might use AI to address all kinds of issues in climate modeling, climate data analysis. There's an interesting paper that came out last February around the idea of, could we go even more aggressive in using AI to beat numerical weather prediction? And their strategy is kind of clever, or not clever, it's just kind of obvious, but it's kind of bold. So on the left-hand side is a traditional pipeline, right? You collect data, you do, say, Kalman filtering to do assimilation, drive the data into your model to harmonize those, run the dynamical core, have standard, say, subgrid scale parameterized processes, predict weather or large statistics, climate, and then do a bunch of post-processing, statistical downscaling, traditional methods. Current groups are trying to plug, machine learning or deep learning into each of these stages as augmentations. But the open question is, can we go even further than that? Can we go directly from, say, a large corpus of observational data to a model that actually predicts outcome, predicts directly the climate in an end-to-end fashion? This hasn't been demonstrated yet, but this is kind of the obvious endpoint if you believe that completely data-driven processes might end up replacing physics-based processes at some point. And I think there's a lot of groups that are kind of tinkering with this idea in many domains. And so this is going to drive a big demand of exploration using AI as a primary compute methodology on big machines. So we see this as becoming an increasingly large fraction of the workloads that we care about. Now, of course, training state-of-the-art AI requires massive computing. You've all seen charts kind of like this. Moore's law is the gray line at the bottom, growing embarrassingly slowly. The blue line is, say, the trend line for computer vision systems, or at least ConvNets, essentially. And the pink line is the trend for transformer-based networks, which is growing much more steeply than even ConvNets, and of course, many, many times faster than Moore's law. And so these are becoming larger and larger computations. Now, one of the things that's driving this is the fact that the observation is that as you increase the scale of these transformer-based models, they continue to increase performance. That is, the loss is less. They're more performant, and this doesn't seem to be slowing down. This idea of scale directly translating into performance, and you can see it in the GPT-3 papers, where as they went over 2 orders of magnitude increase in the number of parameters, the capability of the model, say, to answer questions, it kept increasing, and the model was able to use more and more context that it was trained on. So this is a really positive kind of result. When you look at how they break down the alternatives as they increase, say, the compute capability, what should they increase the most? Should they increase the number of parameters in the model? Should they increase the amount of data, or should they increase, say, the amount of training steps? And what they determine from empirical analysis is that they get more bang for the buck by increasing the model size. So this is driving this extreme scaling up of models, and that is resulting in this kind of exponential growth. And the issue that a lot of people are raising is that as these models become larger and larger, only very few groups can actually afford to train them. In order for the academic community to have access to this, they need access to computing that's not controlled, say, by the handful of tech companies. So this is one of the kind of issues that we're dealing with in terms of why these large exascale machines might be critical national resources for driving AI research, in addition to the traditional scientific mission that we have. Now, in order to feed that, we're also actively collaborating with AI hardware startups. We have a testbed at Argonne that we built over the last couple of years called the National AI Hardware Testbed. And we've got efforts in there from Cerebras. So we were the first customer with a CS1. They're building this wafer scale system. So it takes a single silicon wafer. It does not dice it up. They pattern across the whole thing. So it's got hundreds of thousands of processors. The second generation one, which is coming this fall, has around 850,000 processor cores on this single wafer. And it's got 2.6 trillion transistors on this wafer. And here's the size of it compared to, say, a GPU. So this is basically using the full reticle and then stepping across this and then patterning across the gaps that normally would be used for dicing. And then they drill holes in it so they can put it into a mount and power it from the bottom. So that's one technology. And this kind of a system has been demonstrated in some of our apps at getting speed ups of hundreds or up to 1,000 times faster than GPU. So we think this is a pretty interesting way to go. It has SRAM on the wafer that's only one clock cycle away from the CPU. So it's essentially like all cache or a little bit slower than registers, but it's all there. Specialized processors for AI training, essentially. Well, there's other systems. SambaNova is building something. They use a single reticle for their thing. So it's about 40 billion transistors per package, but they package multiple leaves in the system. And they're also driving a lot of acceleration. It's kind of a coarse-grained data flow system. And we're working with others too, GraphCore, Groq, Habana, and so on. So there's a lot of companies investing in these accelerators. And one of the big open questions is whether or not these accelerators are going to be useful enough in the long term that they add a third layer of computing into these big systems. So one of the issues with these AI accelerators is they're largely standalone, oriented towards AI, pure AI problems. Although we have done some work, we've taken a Cerebrus system, say coupling it to molecular dynamics, running on another machine and having the AI control the simulation or offloading parts of it and back and forth. So this idea of a distributed computing environment that contains classically accelerated machines, maybe GPUs or whatever, as well as these specialized AI systems is certainly of interest. And we have people doing that here at Argonne, at Livermore, other labs. We think that these HPC and AI capabilities need to be very tightly integrated, ideally sharing the same memory space. This is because in surrogate models, you don't want to pay the overhead of switching back and forth between traditional, say, PDE integrators and the AI surrogate component. So you want these kind of in the same memory structure, so it's very efficient, low overhead for context switching. We don't yet know whether matrix-oriented accelerators beyond, the implementation that's either in current GPUs for relatively small matrices, systolic engines or whatever, or these dedicated kind of external accelerators, whether they're going to be a long-term niche. I mean, I hope they are, but we're not so clear. The other thing is we need programming models that actually bridge between the HPC uses of these systems and the AI uses, right? AI is primarily written in Python that code, that's going to compile down to some lower, more efficient thing. But, and while Python's being used as a coordination language in simulations, it's of course not a primary implementation vehicle, and coupling these things is still not easy. So there's a lot of work that needs to be done in the programming models. And I think, therefore, let me just summarize a little bit. So we've got these exascale systems. They're kind of ballistic. They'll be landing. China, of course, is doing the same thing. China will have a couple of machines up by the end of the year, maybe a third machine coming. We think this AI for science and AI grand challenges is going to be a natural kind of successor to the more classically oriented exascale program that we've had. We think surrogates give us an ability to punch much heavier, punch above our weight, I guess, if you want to use that term. So an exascale machine might effectively operate on some problems in the Zeta or possibly Yada performance. But there's a lot of work to be done there about bounding accuracy, understanding uncertainty quantification, optimizing the networks, maybe through network architecture search or automatic transformations of code. So a lot of work needs to be done there. And then we've got AI hardware accelerators in flight. A lot of work that needs to be done there, a lot of community building, a lot of developer access, and getting people to think differently about future HPC applications. So I think I'll stop there. I'm happy to answer questions if there's any time. Let me stop sharing here.
Thank you, Rick. Great presentation. Do you have any thoughts in terms of Argonne's plans or interest with FPGAs?
So we have a group that does FPGAs. We use them a lot in detectors, where we have to do kind of edge computing right next to detectors. And we're part of collaborations, at CERN and so on that use FPGAs a lot. I would say that we keep tinkering with the idea of, if we had a big machine, say 10,000 nodes or something like that, if we had an FPGA on every node, or multiple ones on every node, would we get enough utilization out of the FPGA to make it worth doing that? And so far, the answer has been no. Every time that we've tried, I'm not saying it will never always be no, but every time that we try to find enough examples where the tool chain to go from an application to the FPGA bit file and load it and run and kind of measure that performance and the fraction of apps that could benefit from it, it doesn't turn out in our favor. It doesn't mean it couldn't, and it doesn't mean maybe for certain other workloads it would make sense. Microsoft's Azure has made good progress with FPGAs. Other groups have. So we have small test beds, but we haven't scaled it up. On the other hand, if a vendor was able to show that we could, or community could show that we could get a lot of applications speed up effectively, that would change our minds. But as we go from our current exascale machines to the next round, say we're looking for another, say, factor of 5 and over 4 or 5 years, that's going to be pretty hard to get that lift with FPGAs. That's my guess. FPGA clock rates are still pretty low, and other things.
Let's see. I got a question here. Do you perceive speed up capability? I'm trying to decipher a little bit here. You say that about GPU too.
It's the example of the Brian Sparks human compiler in action right now.
Exactly.
It's working only on a couple cups of coffee. That's my accelerator. Do you perceive speed up capabilities with the FPGAs?
Well, I mean, for any given application, depending on its intensity in traditional floating point. So if you're doing like massive double precision, it's hard to get speed up on FPGAs because the FPGA's base clocks are usually slow and it burns up a lot of gates to implement, say, double precision, right? So where you tend to win on FPGAs is where you're dominated by some other operation, integer operations, bit masking,
lower precision, maybe
low precision inferencing, things like that, right? Now, what's happening in the broader marketplace is companies like Intel and AMD and NVIDIA are putting into GPUs and CPUs, if you're Intel, very efficient, low precision inferencing capabilities like int8 and int4 that, so just for like AI inference, they're going to smoke an FPGA unless you can really customize it, because you're going to have these very high performance integer operations that are maybe a factor of 30 or something faster than the floating point precision on FPGAs. And that's going to be really tough. But it doesn't mean there aren't applications, right? But I think for like mainstream AI, it's going to be tough to beat where GPUs are going or where the dedicated AI accelerators are going.
Okay, thanks. I hope that answered the question. The next one here is codes like NE1 using ML to accelerate quantum chemistry may be superseded by quantum computers one day.
That's likely, but quantum computers have to get useful. I think it's going to be tough, right? So these classical simulations that give us approximate wave function solutions, whether they're DFTs or higher order methods, coupled with AI, you're going to get some big acceleration there. And, depends on the problem. So if you're using it to search, let's say you're you're trying to design something and you're trying to sweep through some large material parameter space or chemical structure parameter space or something, your primary use case is not super accurate simulation. It's trying to sort the wheat from the chaff, right? It's trying to find, and I think AI surrogates are going to be really good at that. Now, maybe when you get down to that small fraction of the search that you now want a very accurate simulation, you could then go over to either higher order methods classically or to quantum simulation. So I think it's going to be a mixture. Quantum simulations are not likely in the near term to be fast for searching, just because you have, it's like you're going to have one problem and you're going to beat on it to get a really accurate answer. But if you need to load up 100 million configurations to run it, quantum is probably not going to be your choice. Because getting each configuration into a quantum machine is tough.
Thank you. And I see Mark's hand is raised. Mark, you have a question for Rick.
Yeah, thanks. Yeah, great talk, Rick. Very, very interesting. And I have a question about essentially the environmental impact of some of these calculations, because you mentioned that training one of those large models was going to cost, I think it was $3 or $4 million. That translates to a lot of power, a lot of carbon. How are we going to improve that?
I think we have to be a little. We have to really look at what it costs to run these big machines in general. So, a machine like Aurora is going to have an annual power budget of probably something like $50 million. And that's going to be the same whether you're running AI or climate simulation. It just depends on, it doesn't really depend on what you're running. It depends on how efficient the machine is going. But let's say it's $50 million a year. You can translate it into a carbon footprint or a dollar footprint or whatever you want. And then the question becomes, well, of that $50 million of burn time, now the operating cost is higher than that because you've got people and maintenance, all that kind of stuff. But let's say you're just worrying about the power budget. How many AI computations are going to do in there? How many traditional simulations? How many cosmology, universe simulations? How many materials design simulations? So on. Every big problem is going to have a big footprint. Mm-hmm. I think the key with the AI things is that, and this is where I think the social issues need to come in, is that most of what we do, almost everything we do in the open labs, is open science. So the outcome of a big cosmology simulation or materials design simulation is public data, public knowledge. I think if you're going to do a big AI calculation on a public machine, that AI result needs to be publicly available. And the beauty of these, say, generative text models, particularly if we can get them to work in materials design or whatever, is that many people can downstream use those models to do interesting work and wrap them and don't have to pay that training cost again. Mm-hmm. And that's very different than, say, a cosmology model, where I run that cosmology model, I get data out of it, right? And people can use that data, but that's a bit different than training an AI model, where I can use it on my own problem and post-process it or maybe tune it at a very small fraction of the cost to originally train it and get some additional benefit, where I can't do that, say, in a traditional simulation. So I actually think that the real issue here is not the cost, it's not the footprint, it's openness. Mm-hmm. And this is what we're not seeing, from the Googles or Microsofts or the so-called OpenAI, which is really Microsoft subsidiary at this point, where, they're doing great things. Don't let me get wrong in that. It's just that the public benefit from that, is going to come via some product that they do, as opposed to the actual technology that comes out of it that could be built on by the academic community.
Great, thanks.
Dan has his hand up, but I'm not the
MC. So. I guess following up on that a little bit. So really, if you're training these AI models, then there's a reusability in it.
That's right.
For others.
That's right.
That these are a trained model, and it's not like they're putting inference through, but they're cranking their data back through that model that's already been trained, which is a much less expense in terms of computation.
Absolutely. Absolutely. And there's been, there are groups like Hugging Face site, which you should go if you're interested in language things. But they've all these transformer models that are pre-trained and made available. You can download them. Some of them run on single GPU machines, right? And you can do inferencing at a very low cost. So I think there's actually a good argument to be made. Yeah, maybe I spend $5-10 million training a model, but if I have 100 or 1,000 users of that model later that don't have to do that work, that's avoided costs, avoided greenhouse gases, avoided.
That's a big win.
It's a huge win, right? So we don't need to focus on the wrong side of it. Now, if you've got groups that are kind of just squandering it, I mean, training it and not making it public, then that's a problem, right? But we have that problem in many other areas. And I think if we can just get the community to be thinking in terms of reuse and what's the real value of these big machines, right? And I see it as actually several ideas, right? One is that just having these machines exist opens our thinking, right? It's like having wilderness. Maybe if you never go there, you know it exists and then you can think about it and you can think about what it would mean to use it, right? So that causes people to expand their thinking, just like existence of quantum machines has caused people to think about new algorithms that maybe get implemented in classical machines. And we all benefit from that just because of the idea was there. So big machines that can be used this way are idea factories. And I think that's a benefit from it. Then this reuse, right? Both of models and reuse of data. And then another one, which we started seeing people, do, and this was mentioned in the previous speaker in the Q&A, sometimes you want to build, proxies or surrogates, say stick in a climate model or cosmology model, and you want a high resolution simulation in which to build that model. Well, this notion of running on a really big machine, a super high resolution simulation, saying combustion, to get the physics understood and so on, maybe train a model and then take that understanding and bring it to lower resolution models, say the industry could use. And that's, again, a reuse concept, right? So I think there's a bunch of arguments for why to do this that kind of have broad public benefit. It's not just the direct reuse of the products, but the fact that it inspires young people. They're time machines in terms of how we think about what's possible. They inspire technology people. If we put these machines in the public sector, then the young people can learn how to use them and train them and build them. And all that expertise is not hidden inside a Facebook or a Google, right? It's out and can be leveraged by the broader economy. But I think there's all kinds of arguments for doing this.
That makes a lot of sense. My real question, that was just sort of based on...
Okay, that's a warm-up, all right.
Yeah, that was a warm-up question, but real quick, what technology is your money on to be the accelerator of the future? Or are we going to continue, let's say 5 years out, are GPUs going to continue to be as much of a big deal as they are now? Or will they be supplanted by something?
Well, this is a big question. The big idea is we know that current deep learning methods need high performance, mostly dense matrix operations. GPUs, as they originally were conceived, are essentially vector engines. Now, what's been happening over the last few years, and you started seeing this, in NVIDIA early on, and now the AMD and the Intel machines have this as well, is building into the GPUs things like systolic arrays or small matrix engines that can do small matrix blocks in parallel. And so they're starting to become better at doing matrix-oriented math than if you think of them just as vector engines. All right. The big question is, if you really went hard over to the matrix side of the world, which pure AI accelerator is essentially optimized for that, what are you giving up in the other part of the space, right? So if you've got traditional scientific applications that are really are more easy to use, they can't use dense matrix operations as well as they can use, say, vector operations or maybe sparse matrix operations. And so we know things that are serialized or thread dominated CPUs, so that's not going to go away. But now we've got these GPUs that are kind of mostly vector engines, but pushing into the matrix space. And then we have these coming from the other side, more matrix oriented engines. And what's going to happen? Are these things going to fuse into some future accelerator device that basically is equally good at vector and matrix? That's my bet, is that we're not going to see a third a third type of engine as much as that we may still have some specialized AI things, pure AI, but in terms of general purpose things, some kind of evolution of accelerators that have excellent vector and excellent matrix and maybe excellent sparse matrix acceleration. That's what we need in some sense. And the reason we want that to be in a tight memory integration with the CPUs, because we don't want to pay the overhead of translating between the memory spaces, right? Right now, these dedicated AI engines, they're beautiful. And I love them, and I love the companies they're making. We're partnering and so on. But, they're separate engines. And if I've got something that's a simulation sitting in CPU land or GPU land, and they want to use that, I have to translate out of that memory space, right? Transfer it over and back and forth. So I'm sloshing things back and forth. I don't view that as the future. I have an axiom about the future, and the future is not stupid. So we have to somehow be clever about this. Maybe the market will help drive it in a clever way, but maybe it's going to be some, engineers figuring it out how to be clever at it.
Thank you. Very good answer. I appreciate it.
Thanks, Dan, for the questions. That's the last one. Thank you, Rick, for an excellent conclusion for day one.
Okay, good luck with your deliberations.
Thank you so much.
Signing off.